Shivaram is not here. I'm presenting today. Yeah.
I'm really excited about SparkR. This is awesome.
Cool. Thanks. Yeah. So I can just wait downstairs.
Okay. Yeah, sounds good. I guess we'll start. We'll wait a little bit more. It looks like people are still coming in. Okay. Alrighty, looks like we're about ready to get started. Thank you very much. This is track C, data science track for Spark Summit. And I'd like to introduce Zongheng Yang from AmpLab, who will be talking about SparkR. One of the most interesting developments that I've seen going out and talking to people in the field is the different kinds of integration of Spark with existing workflows. And given how much data science teams, my teams in particular, I've seen using R, I think that this is a great integration. So, thank you very much, Son.
Thanks for the introduction. Hi, everyone. My name is Zongheng. Today, I'm going to talk about SparkR, enabling interactive data science at scale. I am a third-year undergrad student at Berkeley. I'm a research assistant at AmpLab. This is a joint work with Shivaram, who is a third-year CS PhD student at AmpLab. So this is the agenda of today's talk. I'm going to give you some motivation behind SparkR as a project. Then I'm going to overview Spark and SparkR's API a little bit. And then I'm going to give a live demo on digit classification problem. I'm also going to talk about some details behind the design and implementation of SparkR. If there's time, I will leave some time at the end for questions and answers. So when new users come to Spark, what are some of the key advantages that might come to mind? I think the first thing is that Spark is lightning fast. There are a lot of features, a lot of reasons behind this, but one of the most important things is that Spark supports in-memory computation as much as possible. And the second key advantage of Spark is that it is scalable. In fact, Spark is designed to be a cluster computing engine. So when you have a cluster and when you are running a job, if you are faced with a bigger job size, you can usually expect to throw more machines at your cluster and expect it to handle the bigger job size. And the third key advantage of Spark is that it is highly expressive. And by that, I mean it comes with 3 officially supported language bindings, which are in Scala, Java, and Python. And today, I'm going to talk about a new language binding. And these APIs are highly expressive, concise. It usually contains some functional operators that allows you to focus on solving your problems. So what about R as a programming language? What are some of the key advantages that might come to mind? So the first thing is R is really good at numerical computing. In fact, R is designed to be a it's a programming language designed by statisticians and is very popular among data analysts. Moreover, R comes with an extensive list of very mature and sophisticated packages. For instance, many of the state-of-the-art machine learning algorithms, when they are published in research papers, they usually come with accompanying R package implementation. And the third thing about R is that it fits really well with an interactive workflow. For instance, R comes with R shell, and in R shell you can do some ad hoc analysis and exploratory plotting, for instance. So our motivation is, what if we can combine the best of these two worlds? Traditionally, R suffers from a problem that R's internal is single-threaded, and it is impossible or really hard to write our programs and have them run in a multi-machine distributed fashion. So SparkR is a language binding that combines the best of these two worlds and seamlessly integrates R with Spark. Moreover, we enable interactive native R programs to scale in a distributed setting. So I'm just going to talk a little bit about Spark's API. At a fundamental concept of Spark is this RDD concept, which stands for Resilient Distributed Data Sets. For now, you can think of it as a large collection of data distributed among all the machines in your cluster. There are two kinds of operations defined on an RDD. The first kind of operation is called transformations. For instance, we have this familiar map and filter operator, and also group by key, and a lot of others. The second operation is called actions. For instance, count just returns the number of elements in an RDD. And actions are what really trigger an actual computation in a Spark job. Transformations, on the other hand, it has lazy semantics and it returns a new RDD. So what is the result of combining R and RDD? For those of the Star Wars fans out there, it's of course the R2-D2 robot. But we came up with something better, which is RRDD. At a high level, RRDD is a subclass of RDD which supports a large subset of the operations we have seen so far. For instance, we see that we support this map function and this map partitions functions. And I'm going to talk a little bit more about these aliases, lapply and lapply partition, very soon. SparkR currently also supports this shuffle operations such as group by key and reduce by key. At the center of this list, we see some actions such as collect and cache. And at the bottom of this list, these are operations defined on a Spark context. So for instance, text file is a function that takes in a Spark context and perhaps a HDFS location and just returns an RDD of string. SparkR also supports this broadcast function, which is a notion in Spark that broadcast simply takes in Spark context and a value, and it push this value to all of the executor machines in your cluster. The last function in this list is this include package function. It is new to SparkR. What it does is that it includes, you can give it a third-party R package, and it includes this package in all of your executor machines. So when the executor machines launch R processes, it has all the functions it needs in scope. I'm going to give a demo that makes use of this. So this is a quote from this article here, which just asks, how can I use a loop to do something in R? And the idiomatic answer to that is that you don't. You usually do not use a for loop or a while loop in R. And instead, R provides this a family of apply functions. For instance, the lapply function just stands for list apply. And by including this lapply and lapply partition functions in SparkR, and just to make myself clear, they are actually aliases to the map and map partitions functions. But by including these aliases in SparkR's API, our hope is that we want to make sure the learning curve of existing R users is not too steep. And we want to make R native programmers feel familiar. So let's see how the API works in action. I'm going to walk through line by line this very short word count example. So in word count, the first thing you do is you use this text file function, which takes this SC variable, which is a Spark context, and then you pass in your HDFS location. What it does is that it processes the data and returns an RDD. So the next step, we are using this flatMap function. For those of you who might not know, flatMap is simply a map function followed by a flatten. So it takes this lines RDD here, and then it applies this closure, which I want to stress that is a R native function. what it does is that it uses this native string split function and splits the line by NP space. And this double bracket 1 here is just a nice way to tell R that we want the return result to be a vector. So for instance, if you have a line of hi, all, and one instantiation of this closure will return a vector of these 3 words. And by passing this closure to this SparkR flat map function, we get back words RDD. So the next step, we use this lapply or map function over this words RDD. And again, we are using native R closures here. And this function just put each word into a key value pair, where the key is the word itself and the value is the number 1. So the next step is, of course, by using this reduce by key function. And what it does is that it takes this word count RDD, which is a list of key value pairs, and it take a look at all the keys and put the key, so group by the same word. And then this second argument here, which is a native R plus operation, simply sums up all the ones in the value field. So naturally, what we get back is the total occurrence of one word. And this num-partition is just telling Spark how many output partition to use. And the last step of this word count example is just calling the Spark collect function on this counts RDD. So we might get back data such as this hi, comma 2, and all, comma 1, as an R list. So in summary, I think there are a couple of things this demo shows you. The first is that SparkR enables you to manipulate your HDFS data from within R by using this text file function. And the second thing is a lot of the Spark primitives, such as this flat map function and lapply function, are already available in SparkR. And the third thing is SparkR enables you to integrate your native R code, such as these 2 operations, these 2 closures here, and you can pass these closures into the Spark primitives. So next, I'm going to give a live demo on the digit classification algorithm. We are going to use this MNIST dataset. For those of you who might not know, this is a dataset of hand-returned digits as images. It is actually very popular among machine learning community. So our high-level plan for this demo is just we take this input dataset, which are just images, and we extract and compute 2 things from it. The first thing is this matrix A, which is usually called the feature matrix. And the second thing is this label vector B. Once we have these 2 things, we are going to train a machine learning model such that this distance here is minimized. Once we have trained our machine learning model using SparkR, I'm going to take our model and apply it on some test data set, and we can see how the model fits. Okay, so let's see. I'm just going to log in this RStudio thing. So for those of you who might not know, RStudio is actually a web-based IDE for R. So we have our demo code here. I'm just going to copy and paste and run the first part of it because it takes some time, and then I'm going to walk you through this demo program. Okay, so it is running in this console. So let us start looking at this demo program. And the first thing you do when you are writing a SparkR program is by using this library parenthesis SparkR, which just imports this SparkR package in your environment. And then we also have lines 3 and 4 here, which include the third-party R packages we are going to use. In this case, it's matrix and caret. And on lines 5 and 6, I'm just sourcing some utility functions. On line 8, as you can see, we are having this assignment statement, which just creates a Spark context using this helper function we provide, which is called SparkR.init. What it takes is that it takes in a Spark master URL. And in this case, we are using a local machine with 8 threads. And you can imagine in other cases, you can pass in, for instance, a EC2 Spark master URL. And on line 9, we are just reading some training data into an RDD. And here we are using number of partitions equals 8. The next 2 lines are not too interesting. We are just generating some random stuff. But what is interesting is here on lines 16 and 7. Since this W and B will be used in every pass of our machine learning algorithm, so instead of having the executor to fetch this data every pass, we just simply push it by using this broadcast function. We push it to all of the executors once. So this broadcast function takes in a Spark context and then the value to broadcast. And on line 19 here, we are using this include package I told you before, and it takes in a Spark context. And in this case, since we are going to use this matrix package in our closures very soon, we just, before we pass in the closures to SparkR, we use this line to tell all of the executors to include this package. The next 2 assignments are just simply calculating the feature and the labels. Notice that on line 32 and 33, we make use of these broadcast variables we just created before by calling this value parenthesis broadcast variable. So this is very similar in Scala. In Scala, you can do broadcast variable dot value. And notice that SparkR supports using these broadcast variables in a closure passed to this lapply partition function. So finally, this is the center of the machine learning algorithm. We are just calculating this A transpose A and A transpose B. And this kind of weird operator here is actually a matrix multiply function provided by the matrix package we just included. So since this closure is being executed on each of the executor, the executors need a way to know what kind of packages to include. So at the end, on line 48, we simply solve our linear system. So let's try to apply our machine learning model on some of the test data. And I'm just going to run this part of the code. Okay. So what we do here is we're reading this test data, which is a CSV file, and we fetch the true labels from the test data. Okay, so the test error we got is about 6%. It's not 100%, so I'm good. Yeah, so I want to highlight one key advantage of SparkR's approach here. So in the next part of the demo, I want to show you what are some of the advantages of doing all of this in R versus doing this in Scala or Python. So imagine you are a data analyst, and after doing all of these computations, you might want to do some exploratory plotting or visualizations to see how where your model goes wrong. So there are a lot of existing and mature tools in R that are available for this purpose. And here we are just going to use that carrot package to plot a matrix out of it. Oops, invalid graphic state. Let me just run this. So let me just run this part again. I'm not sure what goes figure. We just.
Do you have a device open?
device. No. I, is this? Anyway, we can skip this part and see. Sorry, I do have another visualization to show you here, and let's see what. If it's, okay. Oh, cool. So, okay. So this piece of code simply looks at what exactly are the images that our machine learning got wrong. So I'm just getting a random image in our data set, and this is the true label of this image is 2, but our algorithm got it wrong to be 7. I actually think it's very close to a 7. Yeah, and we can do this like one more time. So this is actually a 4, but our machine learning got it wrong to be a 0. As you can imagine, if you are mature, if you are very familiar with R, if you are a data analyst, for instance, you can have a lot of packages to use here. So SparkR, the key takeaway here is that SparkR make it really easy to use this kind of tools right in your Spark programs. So before I end this part of demo, let me try this once again. Oops, there it is. Let me just, so this is a confusion matrix, and let me give you the definition of it for those of you who might not know. So if you look at a row I and column J, what that means is that how often the algorithm confuses the true value I, which is the row value, to be the column value J. So it is good to have, so the darker the grid is, the more often the algorithm gets confused. So it is good to have the diagonal to be all dark. So that means our algorithm gets most of the cases correct. But as you can see, the grid here, which has row value 9 and column value 4, so that means our algorithm confuses 9 to be 4 for a lot of times. And there are other cases such as this row value 1 and column 7. So it confuses 1 to be 7 for a lot of times. So again, I want to stress the fact that there are a lot of other cool visualizations and exploratory things that you can do. And some of the R experts out here might know better than me. The key takeaway here is that you can include this kind of packages in your SparkR program, and after doing big data computation on using Spark, you can do this exploratory plotting really easily right away. So let us switch to our presentation, and I want to give you some of the details behind this SparkR project. So I'm going to talk about the data flow of a job. Suppose we have a cluster here. Suppose you have a local machine and 2 worker machines. And what you do first is that you launch a normal R process, such as the R shell. And then you can initialize SparkR by using that library parenthesis SparkR. And what it does is that it initiates a JN9 call, which is a Java native interface call, to your local JVM. And a Java Spark context, a normal Java Spark context will be created in your local JVM. And SparkR will hold on to a reference to that Java Spark context in your local R environment. So for instance, we have seen the SC variable in our word count example, and that SC variable in R is ready for use. So when you have an action, when you actually trigger an action, this Java Spark context will just initialize this Spark executor processes on each of the worker machines. And when the computation arrives, what this Spark executor does is that it forks off a new R worker process locally. So you can see 1 R worker process for each Spark executor. And this R worker process is responsible for taking in the deserialized tasks, which is just R code. And it might also take in some broadcast variables. And a list of R packages to include in the local R environment. So once it has all of this information, the R worker process will just start running the function. And once it gets back the result, it will return the result using these purple pipes here to the Spark executor. So I've been talking about this kind of pipes connecting our worker processes and Spark executor. So I want to show you two aspects behind this kind of similarly complicated communication. The first aspect of it is that how does SparkR capture the user-defined closures? So there's this environment concept in R. An environment in R is simply a mapping between variable names and variable values. So, and each environment can optionally have a parent environment. So when R does a variable lookup, it simply looks at the environment of that variable, and if it cannot find anything, it will just walk up this environment chain. So what SparkR does here is really similar to that. When SparkR is processing a user-defined closure, for instance, as an argument to the group by key function, we just walk up this environment chain and then grab basically every variable in this chain. And then we have this variable and their values wait for serialization. Which brings me to the second aspect of this communication pipes, which is serializing the closures. So there's this very nice to use save function defined in R. R provides this function to taking arbitrary R objects, and the output of this function is just an byte array. So for instance, when you have an R shell and when you are exiting the R shell, you will get a prompt asking you whether or not to save your session. And this save function is actually used in that process. So instead of dumping this byte array to this, SparkR uses this function to get the byte arrays of closures and then ship these byte arrays across the network. So that kind of ends the implementation part of my presentation. We made our first alpha developer release earlier this year in January, and we also include a really cool one-line install method that you can play around with. Also on GitHub, you can find some easy to set up scripts. So SparkR does support running applications on EC2 now. And we have also ported all of the standard Spark examples, such as k-means, to SparkR. So that kind of shows the completeness of SparkR API. And also available is this MNIST demo program I just showed you. We also have some instructions on the Hadoop 2 and Maven build, and that might be very useful for some of the users. I want to highlight that SparkR is actually really lightweight. There's actually less than 300 lines of Scala code and about 700 lines of R code. And I think that's a testament to the fact that Spark is really easy to extend. As for future work, I want to highlight these three things. The first thing is enable this better MLlib integration from within SparkR. So for instance, instead of hand-rolling your own machine learning algorithms, such as the MNIST demo program I just showed you, what if we can just call MLlib from within a SparkR program? What if we can just call k-means.chain and then pass in some data? That would be much easier. And the second thing is R has this very popular data structure called data frames. And currently SparkR only supports lists and vectors in R. So it would be really nice to support this data frame. I think tomorrow Christopher will talk about one of these efforts. And also another direction is that since SparkSQL is now released, and SparkSQL comes with this schema RDD concept, and schema RDD is in fact a table equipped with a schema. So it might also be worthwhile to look into using schema RDD to provide this data frame support. And lastly, I want to mention one performance optimization that we can do. So instead of forking off these R worker processes which are short-lived, we can actually implement some daemon R processes and have them running in the background. And this will reduce the cost of context switching and creating new threads. In summary, my talk today presents SparkR, which enables the seamless integration between R and Spark. It also scales our programs in a distributed fashion. From what I know, I think nowadays any other tools is really, so we don't really have a method to do this, to run our programs in a distributed setting. And finally, SparkR combines the scalability of Spark and the utility of R. So on this link, you can find our GitHub repo here. It contains all of the code and examples I mentioned. Please feel free to play around with it and submit any issues or questions on GitHub. Or you can alternatively email me or Shivaram or perhaps the Spark user list. That is my talk today. Thank you very much. Questions? Yeah. Okay. I'm happy to take any questions.
So if you're putting this on your own cluster, do you need to have the R executable installed on each node within the cluster?
So the question is, if we want to run SparkR on our own cluster, do we need to install R on each of the worker machines? And the answer is yes.
So at some point, are you looking to implement a factor-like data type?
Factor-like data type. Yeah. Okay. It's not currently on our roadmap yet, but it would be good to look into it.
What's the overhead from having to launch all these R interpreters all the time?
The question is, what is the overhead of launching these R interpreters and R processes all the time? We haven't done a very rigorous benchmark yet, but we have done some small experiments, and it's actually impacting the performance a lot. So that's why we might want to look into like implementing these daemon R processes. And for your information, this approach is actually taken by PySpark.
How does it use cluster computing? Like you solve that equation,
Yes.
you pass all this thing onto two machines. So how does it use two machines? Because what I gather is both are doing the same thing. So how does it use the two machines cluster?
Oh, so the question is, in the data flow diagram, how do we make use of the parallelism provided by two machines?
Yeah.
Is that correct? Okay. So I think, so there are two things. The first thing is, this is actually the same as a Spark data flow model. So in Spark, if you have a big data set and if you partition it in two partitions, you can actually independently operate and compute something on this each of these two partitions. So that's one thing. And the other thing is, instead of having Spark to compute it, we launch these individual R worker processes. And these R worker processes are what actually carry out the computation.
So that computation has to be parallelized, like matrix multiplication. The computation you are doing.
Yes, you have to come up with a way to partition your data, and you have to structure an algorithm to do that.
So closures in R can reference their inputs, but also any data in the environment they were created in. When you serialize them, is the environment serialized as well?
So the question is, in our closures, variables in closures can reference variables in other environments, and the question is whether or not we serialize those environments as well. So I believe the current implementation actually just fetches all variables in those environments. So that's kind of redundant. So in the future, we might want to, like filter out those variables in some way, and then just leave the reference variables in the closures. That's a good question.
One other quick question.
Yeah.
It seems like it's been a few months since there was much activity on the GitHub repo,
Yes.
But it sounds like you're still doing things. So I just wanted to check sort of the status and energy behind the project.
Sure. Some of you may have already known a company called Alteryx actually announced a partnership with Databricks this morning, And these two companies will invest some more engineering resources in developing SparkR. So I encourage you to check out that press release. And Patrick Randall will talk about this a little bit more in tomorrow's presentation. Thank you.